Hey, thank you for the introduction and invitation, and thank you everyone for joining. So today, I'm going to tell you about a framework to study for studying low energy effective theories for metals, including Fermi liquid and non-Fermi liquids. So in condensed matter physics, we of course know the UV physics very well, but usually the physics in the intermediate energy scale is notoriously complicated and hard. But then as we go to low energy limit, simplicity reemerges, and often we can capture the ground state and low-lying excitations using rather simple effective theories that can be tractable. And the goal of the effective theory is not to capture the physics in the entire energy scale, but captures the low energy physics within certain accuracy. And in achieving this goal, the powerful language that has been developed in 20th century is the renormalizable field theory. So as we know, different UV theories can capture the same IR physics. So there's a little bit of freedom in what UV theory we should use to capture the IR physics. And a renormalizable field theory is the simplest theory that captures the IR physics within each universality class. It is simplest in that it contains the smallest number of parameters to be fixed in terms of some experiments. And once you fix them, you can reproduce all other low energy observers within errors that goes to zero as powers of energy scale, mu. So where mu is the energy scale at which you probe the system, and lambda is some UV cutoff scale. Okay. So examples include, say, the FIFO theory for the Ising criticality and the standard model of our own universe. They are renormalizable field theories. And in the conventional, say, relativistic field theories, we learn that we only need to include a very small set of parameters within such renormalizable field theories. They are the couplings associated with marginal and relevant couplings, where the couplings have a non-negative scaling dimensions. In metals, the notion of a renormalizable field theory is more subtle and in an interesting way. And that is due to the fact that there are lots of low energy degrees freedom, as is shown, say, in this finite specific coefficient. So in the presence of, say, Fermi surface, there are continuously many gapless degrees freedom living on the Fermi surface. So it's not hard to imagine that the number of parameters that we have to include within the renormalizable field theory has to be kind of infinite. It's a function worth of information that we have to include, like shape of the Fermi surface and angle-dependent Fermi velocity, and so on. Okay, and you may wonder whether one has to include all those information. And in general, the answer is yes, because even at low energies, fermions can undergo large angle scatterings, right? Even in the normal state, if there are strong superconducting fluctuations, Cooper pairs that K and momentum minus K can be scattered across the entire Fermi surface while staying close to the Fermi surface. So in this case, one in principle needs to know the size of the Fermi surface and shape and the variations of the couplings along the Fermi surface to properly capture the low energy physics. So this fact that you have to include short distance information, like Fermi momentum, to capture the low energy physics has been vaguely called UV-IR mixing. Okay. So there are interesting consequences of such UV-IR mixing. So first is that you cannot construct renormalizable field theory just by including couplings that have non-negative scaling dimension. There are couplings that have negative scaling dimension, but give rise to infrared singularities. Okay, if that is the case, you have to include those couplings for understanding low energy physics. So I will tell you in more detail a little bit later, but in a scaling that I will introduce a little bit later, the 4-fermion coupling, say, has a scaling dimension, negative scaling dimension. So naively, so you may dismiss it as an irrelevant coupling. So that is often what has been done in the study of non-Fermi liquids. However, the contributions of those 4-fermion coupling to quantum processes, such as the one drawn here, that kind of give rise to anomalous dimension of some composite operator, is not only proportional to the coupling itself, but also the phase space volume, where the fermions can go into at low energy within the loop. Okay, so as a result, the size of Fermi surface, such as like KF, explicitly enters in the quantum correction. So what controls the strength of quantum correction is some combination of KF and coupling. And as a result, even those couplings that have negative scaling dimension are effectively promoted to marginal or even relevant couplings. And therefore, this seemingly irrelevant couplings can change the low energy physics in a qualitative way. We can, for example, lower the emergent symmetry compared to the one that where you don't include such couplings. So what we want is a theoretical framework that includes all universal low energy information. But we want to do it in the minimal way, in the sense of renormalizable field theory. And this is the main subject of this talk. And this framework, called field-theoretic functional RG, is not what is called patch theory. Patch theory that has been mostly used for non-Fermi liquid is the framework where you focus on some particular portions of the Fermi surface, hoping that mixing between different patches are not important. So patch theory is not, I would say, enough to capture the full low energy physics. And this is also not the exact functional RG. So there are exact beta functions that keep track of the flow of exact vortex function. It would be great if we can solve those exact RG equations. However, it is usually too difficult to solve in a controlled way. And also, we don't really want to know the full vortex function because it contains a lot of UV information that are not universal. So we want to keep all the low energy information, but in the minimal way. So let me first apply or introduce this for Fermi liquids as a warm-up. So this work was done with Hanma, and the story is posted in this archive paper earlier this year. So in Fermi liquids, even when there are strong interactions, single particle excitations created close to the Fermi surface have long lifetime. And as a result, the many-body eigenstates are still labeled by the occupation number of some single particle excitations called quasi-particle. So this lambda form liquid theory captures that. You have the quadratic term, but also you have a two-body interaction. But two-body interaction is such that this quasi-particle interact, but in a way they don't exchange momentum, right? And this captures the fact that the phase space for low energy electron to go into at low energy is very limited. So essentially, besides the BCS channel that is not written here, only way that fermion can stay close to Fermi surface to go back to its original momentum state. However, this theory, as it is written, is non-local in real space because this interaction involves only two momentum sums. If you write in the real space, it represents an interaction between two fermions that are arbitrarily far from each other as far as their center mass position is preserved. This electron can scatter from one location to another location. The reason why this theory is non-local is because it's a fixed point theory that is valid strictly at zero energy limit. In other words, in this theory, we take the zero energy limit first before we look at for the fixed momentum, right? So this theory is a fixed point theory in the renormalization group sense, as was discussed by Shankar and Polchinski. However, in order to understand physics at non-zero energy, small but non-zero energy, you'd like to have an effective theory that is valid at and below some non-zero energy scale. And such effective theory must be a local theory at length scale larger than the inverse of the energy scale. And that's what we would like to construct. So let's start with, say, some genetic UV theory of fermions interacting with each other through a short-range four-fermion coupling, which is function of momentum. So here I have two momentum indices in the four-fermion coupling function, where the lower two momentum are the momenta of incoming electron, and upper two momenta are those of outgoing electrons with spin sigma 1 to sigma 4. Okay, and for local theory, this interaction must be an analytic function of those momenta. Now, as Shankar taught us, at low energy, we want to focus on those electrons near the Fermi surface. So let me label those low energy fermions in terms of angle around the Fermi surface. For now, for simplicity, let me focus on two-dimensional, two-space dimension with the, say, spherical symmetry, but this is not essential. So theta is the angle around the Fermi surface, and this kappa represent the radial distance away from the Fermi surface. Okay, so at low energy, theta can be from 0 to 2 pi, but kappa is much smaller than UV cutoff scale. And here I want to note that this kf, factor of kf, mathematically arises from the Jacobian, where you change variable from kx to ky into this polar coordinate, right? But also, this kf kind of plays the role of metric in the momentum space along the direction of the Fermi surface, right? Kf, so theta is a compact variable that runs from 0 to 2 pi, but kf encodes the information about how many low energy gapless modes there are in a given, say, system, with finite system. Right? So KF has that notion. And for this reason, I want to view KF as one of the low energy data, or you may call it even coupling or some parameters of the theory. The different metals have different KF, for example. Of course, we also need to specify the Fermi velocity to specify this this theory. And in terms of two-body interaction, at low energy, there are two channels that need to be included. Again, following the Shankar's scheme. The first one is the fold scattering, where electrons, say, at angle theta, and angle theta prime interact without exchanging momentum. That's the fold scattering that was included in the Fermi liquid theory. But as I mentioned, if you only include the fold scattering, that leads to non-local theory. So to make the theory local, we would like to allow non-fold scattering with a small but non-zero momentum transfer Q. Okay, so this term here, you can just look at the picture. Describes the process where electron near angle theta and another electron near angle theta prime exchange momentum Q to be scattered close to its original momentum. Of course, in order for those electrons to stay close to the Fermi surface below certain energy cutoff, this Q has to be smaller than energy cutoff. But the point is that this Q is can be still non-zero. Okay, here in this interaction, I have two powers of KF, and this is due to the fact that the location of two electrons, say two incoming electrons, can be anywhere on the Fermi surface, right? So associate with theta and theta prime, there's two factors of measure along the Fermi surface. And then, of course, the third momentum, Q, is of course can be is arbitrary, but it has to be small. So therefore, the measure associated with a Q comes with a factor of Q instead of KF, right? So that is important details. Another channel that we have to include at low energy is the BCS channel, where pairs of electron at momentum Kn minus K is scattered to Pn minus P. Okay, but again, in order for the scattering to be local in real space, we need to allow the Cooper pairs to have small but non-zero center of mass momentum. So here I have initially Cooper pair at angle theta and theta plus pi with zero center of mass momentum, but then I boost them to give non-zero center of mass momentum capital Q. And these Cooper pairs with a net momentum Q now can be scattered into other locations with the same center of mass momentum at angle theta prime. Okay, again, the center of mass momentum capital Q is small, so that's why the phase space for Q is suppressed linearly like this. But the angle theta and theta prime can be anywhere on the Fermi surface. That's why there's two factors of KF. So I just collected all the terms that are allowed at low energy, even though it looks complicated. Its most complicated part is the indices here. And then one can ask, under scale transformation, how does the action transform at the tree level? Okay, so we lower the energy of electron by some factor of e to the minus dl. dl is some small positive rescaling factor. And when we do that, we have to lower the radial momentum with respect to the Fermi surface in the same way. Okay. And then, as you can see, as this electron receives some momentum q, the energy of the final momentum also changes linearly in q, generically, right? So therefore, we have to rescale the momentum transfer in the same manner. And similarly, the central mass momentum of the Cooper pair need to be rescaled by the same factor. And then one can show that under this scale transformation, there's a unique choice of scaling of the field, and under that choice, the action action is transformed into itself with the new parameters in the theory, where kf become larger by factor of e to the dl, whereas this four fermion coupling become smaller by factor of e to the minus dl. Okay, so where does this flow of kf come from? So it comes from the fact that, when electron at angle theta absorb momentum q, its angle changes by order of q over kf, right? Here. So therefore, when q becomes smaller, effectively, it's as if kf becomes larger. Okay, so in other words, increasing kf reflects the fact that with the decreasing momentum transfer, the number of patches that can be connected with this small momentum transfer increases. Number of effectively decoupled patches increases. So that's the kf. And also, this four fermion coupling has scaling dimension -1. So you may ask, how is this comparable with Shankar's scheme, where we learned that, say, fold scattering and BCS couplings are marginal at the tree level. This factor actually comes from this measure, factor of Q in the momentum transfer. Okay, so even in the Shankar's RD, as we integrate out the high energy mode and make the shell close the Fermi surface thinner and thinner, you know that the phase space for the near fold scattering amplitude diminishes. Okay, so that is encoded in this measure. So if you include this measure within the local theory, you will have to assign scaling dimension -1 to the four fermion coupling. Okay. So in short, in the scheme, if you are dealing with, say, non-local theory where Q is fixed to be 0, then you don't have such suppression. But in the local theory where you allow the momentum transfer to be non-zero, this is inevitable. Okay. So it is in this sense that the four fermion coupling has a negative scaling dimension. But interestingly, the kf grows as if it's a relevant parameter of the theory at the tree level. So if there is any question, please interrupt me anytime. Okay, so
maybe just something very naive. Is there then some way to think about things like Latinger volume being preserved under interactions, or
yeah,
how one would state this in this case, in which case
so
is
here,
scaling?
yeah, here I'm already expanding around the kf, and then here, say, in the presence of spherical symmetry, kf is not renormalized, so that Latinger theorem is already already there. So we are, and then we are only looking at the excitation relative to the momentum relative to the Fermi momentum. So, but in yeah. So running KF is not in contradiction with the Lattinder theorem. And Lattinder theorem just says that the singularity of the Green's function, the renormalized Fermi surface is same as the volume doesn't change, and it is already there.
Could I also ask? Hi, by the way, I'm Walter. So if the Fermi surface was not spherical, maybe then things become even clearer. Then I guess what would replace KF in your analysis would be something like the local curvature on the Fermi surface, not the overall size of the whole thing.
Yeah. So right? Yeah. So in the general cases, KF would be function of theta, and then you can still introduce kappa as the distance away from the Fermi surface. But then in general, KF as a function of theta will get renormalized, but in a way that the volume enclosed by KF is conserved.
Yeah, the total
total
volume of the Fermi surface. Yeah, no, was just wondering the scale that enters here. If the Fermi surface was not just spherical, where you have only one KF, if you rescale things, what really matters isn't it the local curvature in your patches?
Oh, okay. Sorry, I misunderstood. So in general case, KF would be function of theta, right?
Right. Yeah.
But then the under the rescaling, this KF. So here we are not rescaling So we are not rescaling the angle theta. So angle is regarded as dimensionless, which is forced by the fact that this angle appears as a sine and cosine. And then locally, this KF, this expression still remains valid because locally, the change of the angle is still only sensitive to KF at that angle. Right? So it's as if KF at each angle is dilated by the same factor.
Yeah.
So
yeah, I think that's fine for the moment. I didn't want to interrupt you too long.
Yeah. Okay, thank you. Yeah. So here, the interesting thing is that the overall action here. So this KF has scaling dimension 1, lambda has scaling dimension -1. So if you look at this action, because KF has scaling dimension 1, under this scale transformation, S itself is not invariant. S action is growing in so to speak in magnitude, and this is due to the fact that the number of gapless modes, when it is measured in the unit of typical momentum transfer Q, number of patches connected by typical momentum transfer Q increases. And then this quartic coupling, say, although lambda has scaling dimension -1, this KF has a scaling dimension 2. So therefore, as a result, the quartic coupling also has a net scaling dimension 1. So in this sense, both kinetic term and quartic interaction scaled in the same way at the tree level. So this is how one would reproduce the marginality of the four-forming coupling. So they are comparable. Although coupling itself diminishes, the phase space that these electrons can explore at low energy increases faster than the phase space allowed for the quadratic term. Therefore, quartic interactions are marginal in this sense. Okay, so that is the point. So, so now we can include the quantum corrections. So here I have written down the beta functional. It looks rather complicated, but again, it's because of the complicated indices. And actually, this I have to mention actually also that this coupling, say near fold scattering amplitude, should be now function of 4 angles in general. Okay, so in the lambda form liquid theory, it's function of only 2 angles, right? Because the momentum transfer is 0. But here there are 2 extra parameters because Q, the momentum transfer is non-zero and its magnitude, and also angle of Q also is additional parameter. Okay, so that's why we need to specify theta, theta prime here, theta and theta prime, and magnitude of Q and angle of Q. Okay, so angle of Q is denoted by phi. Alternatively, you can just specify the angle of the 2 incoming fermions and 2 outgoing fermions. Okay, so in this sense, coupling functions are functions of 4 angles. And this is the, say, one loop beta functional for those coupling functions. Here, lambda tilde is the dimensionless coupling because lambda has the dimension -1. I multiply it with the scale to make it dimensionless. And the first term here, so here L is the logarithmic length scale. As the energy scale mu decreases, L increases. So the first term minus lambda, as usual, captures the fact that this has scaling dimension -1. It's at the tree level. And then this term that is square quadratic in lambda is the one loop correction, where particle hole pair near angle theta1 carrying momentum q is scattered into, say, virtual particle pair with the same momentum q, but that can be created anywhere around the Fermi surface at angle theta, and theta is summed over to finally go to the final state near theta2. So the second line just represents this quantum correction. And there are two interesting aspects. First of all, the phase space volume for the intermediate particle hole pair scales with kf over mu. And this, again, the angle for the intermediate fermion can be anything between 0 and 2 pi, but again, kf over mu is acts as running phase space for those particle hole pair, right? And this the reason why it appears as kf over mu is because kf, as I said, is it's a relevant parameters, right? It grows when it is measured in the unit of your floating energy scale mu. Okay, so that's the first interesting aspect. And then second part is dependence on q and mu. So here, if you set q to 0 explicitly, then this quantum correction vanishes, and this is consistent with the fact that the strict fold scattering amplitude is marginal. But at non-zero q, there are non-trivial quantum corrections. And at a given mu, the largest quantum correction arises when q is order of mu. Okay, so in other words, at energy scale mu, if the momentum transfer is comparable to that energy scale, the non-fold scatterings actually renormalize your coupling function in a non-trivial way. Okay, so although it is irrelevant by power counting, its phase space grows as we go to low energy limit. So this is and then in a sense, these two effects compensate to make this into marginal coupling. So one way to view it is to introduce new dimensionless coupling by multiplying the lambda with phase space volume kf over mu. And then this is now scaling dimension 0, say at the tree level, and this is beta functional involves only quadratic term like this. Okay, so here F is a matrix that depends on two angles, theta 1 and theta 2, for the location of this particle pair, and Q and phi represent the magnitude and angle of the momentum transfer. Okay, and this is the one-loop beta functional of those near forward scattering amplitude. And you can solve this beta functional, and we can trust this at recoupling. And recoupling, the coupling function flows as the energy scale is lowered, and in the low energy limit, it settles into some universal function. It's a function of Q over mu. Okay, so in order, and this is an actual functional RG flow. You say in this example, we start with say S wave interaction where UV coupling is independent of momenta, and nonetheless, as energy is lower, the coupling function acquires some non-trivial dependence on momentum. And when we plot that as a function of rescaled momentum in the unit of energy scale, it flows to this fixed profile. Okay, and this fixed coupling function is invariant under the simultaneous rescaling of momentum transfer and energy. This is when the UV interaction is repulsive. When UV interaction is attractive, say in the particle-hole channel, it becomes more attractive at non-zero momentum, although the strict forward scattering limit is not renormalized. Non-forward scattering channel get renormalized. But if the UV coupling is strong beyond certain critical strengths and is attractive, and it turns out that this coupling function exhibit a runaway flow, just as there is a instability. Of course, this is a perturbative calculation, so strictly speaking, we don't know for sure. It can be just sign or breakdown of our perturbative calculation, but also it could imply some instability in the particle hole channel with a non-zero Q channel, so with some density wave instabilities.
So just to understand, Sung-Sik, should I think of this F basically as what would be the Landau parameters if I had sort of ignored all this Q and phi dependence?
Yeah. So this Q equals 0 is the Landau parameter. And then this non-zero Q is the small angle near forward scattering amplitude. And so experimentally, if you can measure those vortex function as a function of angle, and then as you lower the energy, you also lower the momentum transfer, and then this coupling function takes some scaling invariant form in that scaling limit.
So, and to understand the point you made about the instability, so if what you're saying basically, if my Landau parameter, Landau parameters will have this Pomeranchuk instability if they are sufficiently negative, and even if you're ignoring the momentum transfer, right?
Yeah.
But then you're saying basically, even if that is not, below or beyond the threshold in which you would induce the usual Pomeranchuk instability, this extra flow of the finite Q part can lead to a different instability, or
I think this is a bit different because this instability is in the non-zero Q. Whereas, I mean, exactly where the Q for instability is depends on the precise band dispersion, but generically, the largest flow is at the non-zero Q. So it is some kind of density wave instabilities. It can break some rotation symmetry, but it will generically breaks the translational invariance too.
Okay, now I'm a bit confused. Actually, I also thought that what you describe here might be Pomeranchuk instability, which can be formulated just in terms of the Landau parameters. But of course, the Landau parameters are also uniquely related, usually to the scattering amplitudes. And the difference is just if you come from the two-particle vertex, right? One you get in the static small q limit, and the other in the dynamic small q limit. Do you know what I'm referring to? And so
I think
sorry. Yeah, please.
Yeah, I think the Pomeranch instability can be also understood. For example, as you make the UV coupling more and more attractive gradually, it turns out that first instability happens at Q equals 0. Okay, and and probably that is related to the Pomeranch instability.
Yeah. So Pomeranchuk instability is driven by a Q equals 0 that is forward scattering interaction, while a density wave with some finite wave vector doesn't come from forward scattering, if I'm not mistaken. You need interactions that transfer some finite momentum Q. Right. So I don't see that you can have the density waves here, but I would expect that you somehow get the Pomeranchuk instabilities if you have sufficiently strongly attractive forward scattering couplings.
Okay, so let me try to make it clear. So suppose I have some UV coupling function. It's a function of some momentum Q, right? And it's some smooth function. Now, under this function RG flow, this coupling as a function of Q evolves. So as energy mu is lower, this coupling function shape and its magnitude changes, right? And you can ask whether this coupling function exhibit any runaway flow at certain Q, right? Okay, if the UV coupling function is not attractive enough, that doesn't happen anyway. That means it flows to the fixed point, which is lambda from liquid theory. But if the UV coupling is sufficiently attractive, the IR coupling function diverges, and it can diverge at certain Q first, okay? And the momentum at which first divergence appear depends on the strength of UV coupling and band dispersion. Okay? Now, if the attractive interaction is very strong, then at least the perturbative calculation suggests that first instability happens at non-zero Q. Okay? That would be, at face value, imply an instability in some density wave channels. But if interaction is only critically attractive, right? If you tune your interaction at the borderline between stable form liquid and this unstable region, at the critical value of attractive interaction, the interaction diverges at Q equals 0, but in the mu equals 0 limit. This is like the critical temperature is also 0, but instability happens at Q equals 0. So this is what this perturbative beta functions suggest.
Okay, thank you.
Can I just ask one quick question as well?
Sure.
So I remember, in the 70s, when they try to look at heat capacity of helium-3, right? And they found the correction to, you know, they found that it's not linear in T, and there's a strong correction to T squared log T, right? And the solution to this is to add in, to modify your Fermi liquid theory to introduce finite Q dependence. And those finite Q dependence come precisely from the Berg-Schrieffer type diagram, right? The Donia Engelsberg and Sebastian, no, what are the authors that did this? I think it was, yes, it was Sebastian and Engelsberg who sort of introduced this. What they say is that the Fermi liquid theory itself is not sufficient because the corrections to heat capacity is T squared divided by T by TF squared, right? To the heat capacity. So they say if you now introduce this finite Q dependence, which involves the curvature in Q square, that will explain the experiment, which gives rise to T squared log T dependence. And so, but remember in those work, the Q go to 0 is typically the maximum, and then as you go to Q, you will decrease the functions. So it's not, so I'm just a bit confused. In your calculation, it shows like the strongest is at Q go to 0. The weakest point is at Q go to 0, and it becomes stronger at finite Q.
Yeah. So so I haven't told you about the BCS channel, but in the BCS channel, as we know, indeed the strongest channel is Q equal central mass momentum equals 0 channel. Okay?
Yeah. But what they're studying is just the Berg-Schrieffer diagram, right? It's really a particle channel. It's one type of particle channel where you have exchange on top and exchange at the bottom. You just put in a band of exchange. They're exchanging either zero sum or the spin paramagnon. Right? They're not exchanging particle-particle channel.
I see. Okay.
Yeah.
Mm-hmm. Yeah. So
wait. So you are calculating the Landau function f. Is it? When Q goes to 0, this is a Landau function.
Yes.
Okay. Then I understand. I think what they're calculating is the A, which is F divided by 1 plus F. Mm-hmm. Okay.
So So I think maybe Q squared log T is I think to the leading order in that case, from liquid theory is still correct, right? In that it captures the leading behavior, but this maybe leading subleading term. In order to capture this, you have to go beyond the form liquid theory. In that calculation of specific heat, but I think instabilities like this, if this really signifies an instability, in order to understand, you really have to go beyond the form liquid exact for the scattering limit.
Yeah, I mean, it's just that they cannot extend the data. You know, if T divided by TF square, the T in helium-3 is like millikelvin and TF is 5 Kelvin. T divided by TF square is insignificant contributions to the leading order in Fermi liquid, which is constant in T, right? Mm-hmm. So you must have something else small. Mm-hmm. And that comes from the curvature of this finite Q. But it is my bad. I misunderstood this. I think what they calculate is A, which is F divided by 1 plus F, and it is consistent with your analysis. Okay, sorry to interrupt.
No, that's fine. So in the pairing channel briefly, again, you can look at the flow equations of the BCS coupling at general central mass momentum. And as we know, at Q equals 0 channel, there's a BCS instability. The coupling grows logarithmically if the UV coupling has some attractive channel. But before the instability sets in, there is also Q over mu scaling at non-zero Q. In particular, if you subtract the logarithmic part at non-zero Q, this difference in the inverse of the pairing interaction is scale invariant when you simultaneously lower the energy and lower the center of mass momentum. But still, the most important zeroth order effect is the instability present at Q equals 0, as was pointed out by Shankar and many others. Okay, so this was for form liquid, and I was planning to discuss a bit about non-form liquid, but I'm not sure how I'm doing in terms of time. I can.
Yeah, so in principle, you have 5 minutes, but you can take a bit extra time if you can.
Okay.
Maybe in 15 minutes, that would be good.
Okay, yeah, I will try to finish in 15 minutes. So the story on non-form liquid is based on the work with these gentlemen, Francisco, Anton, Ashu, and Andres, posted in this paper. So, of course, the real interest for us lies in non-form liquid because this is less well understood, especially when metals are tuned close to quantum critical points. These gapless electrons are coupled with some collecting modes, which are also gapless. And if the coupling is strong enough, it destroys the coherence of quasi-particle, and you have anomalous behavior in the normal states, as we all are familiar. And there are also interesting enhancement of superconductivity at quantum critical point. The conventional law is that at quantum critical point, superconductivity is enhanced because those collecting modes act as a glue that bind electrons more strongly into Cooper pairs. However, this is not completely obvious because at the same time, the collecting mode makes electron incoherent, okay? And therefore, it broadens the spectral weight of, say, electrons that are near the Fermi surface. And such incoherent effect is usually pair breaking. In the field theory language, when electron acquires large anomalous dimensions, accordingly, the composite operator also have anomalous dimension, right? So therefore, say, four-fermion coupling become more irrelevant, suppressing superconducting stability. So in priori, it's not clear whether the presence of such collecting mode, critical collecting mode, enhance superconductivity or suppress superconductivity. So in order to, answer those questions, we studied the non-form liquid state that arises at the anti-ferromagnetic quantum critical point in 2+1 dimension, mainly because this is something that can be solved even in 2+1 dimension, which is not usually possible. So here I'm considering a second order phase transition within metal, say, that has a fourfold rotation symmetry into a collinear anti-ferromagnetic long-range order with, say, commensurate wave vector, pi, say, and at the critical point, electrons that can be connected by this ordering vector are strongly coupled with this anti-ferromagnetic spin fluctuations. So people have studied so-called hotspot theory in the spirit of the patch theory, because interactions are most strong near the hotspot. Maybe we can understand the essence of the physics by focusing on the region close to the hotspot. However, in order to understand, say, the role of superconducting fluctuation, you have to include the entire Fermi surface, because Cooper pairs that are near the hotspot can be scattered away from the hotspot, and cold and hot electrons mix with each other. And you would want to understand the interplay between all gapless degrees freedom. So in order to do that, again, you have to include the entire Fermi surface. So here, instead of studying the hotspot theory, we consider the entire Fermi surface. And here we divided the Fermi surface into 8 segments. And each segment include only one hotspot here. And if I specify the shape and the Fermi velocity in segment 1, or other segments are related by symmetry. Okay, so here I have specified, say, Fermi velocity as a function of momentum along the Fermi surface. Say near hotspot 1, I have chosen my coordinate system such that ky is along the q vector, kx is perpendicular to q vector, and I use kx as a label of the Fermi surface. So the Fermi velocity is a function of kx. Furthermore, the shape of the Fermi surface is specified by another function, little v. So the Fermi surface is at when this ky equals minus v kx, but v itself is a function of kx. So therefore, Fermi surface is in general a curved line like this. I call this v as a nesting angle, because if v was 0, that means in segment 1, Fermi surface is perpendicular to q vector, and so is the Fermi surface near hotspot 4. So in that case, the Fermi surfaces connected by the q vector are perfectly nested. So, but in general, v is non-zero, and furthermore, is momentum dependent. So v kind of denotes the deviation away from the perfect nesting. Okay, so, and here there's no, full SO2 rotation symmetry, so I have to keep these functions as general function. So, I mean, here details are not important. Here in the first line is the kinetic term of electron in each segments n with spin sigma, and if there's a flavor j, but you can ignore flavor. And the second line is the Yukawa coupling, where electron in one segment can be scattered into another segments by absorbing or emitting spin fluctuations with momentum q, where this little q is measured away from this ordering wave vector. But here, the important thing is that this Yukawa coupling is also a function of momentum along the Fermi surface. So this Kn denotes the momentum momentum component that I use as a label of Fermi surface in segments n. Okay, and furthermore, this 4-fermion coupling is also a function of momentum along the Fermi surface. So another important point is often this 4-fermion coupling has been ignored because within the patch theory, within the hotspot theory, this lambda has a scaling dimension -1 for the same reason that I discussed. So it seems to be irrelevant. However, within the renormalizable field theory, you have to include it because this can give rise to logarithmic divergence and actually is responsible for the superconducting instability. So you cannot understand the low energy physics correctly without including four-Fermi uncoupling. So ideally, the goal is to understand the full functional RG flow of this coupling function, right? So it's an infinite-dimensional space of coupling. So this axis here is the axis of free fermion, right? Here I specify the shape of the Fermi surface and the Fermi velocity. But then Landau theory includes the Landau theory is living in this space with the non-zero lambda. So if you now turn on short-range four-Fermion coupling function, then we know there's a manifold of Fermi liquids, right? Labeled by the this coupling function. But we know in the presence of attractive interaction in the pairing channel, this Fermi liquid is unstable and flows toward the superconducting state. But this flow is a logarithmic flow, at least in the near the Fermi liquid fixed point. Manifold of Fermi liquid fixed point. Now, if we turn on the interaction between electrons and the spin fluctuation, which is this Yukawa coupling function, this is strictly relevant. So therefore, this vertical flow is a power law flow, much faster flow, and presumably it will flows close to another manifold of non-Fermi liquid fixed points. And depending on whether this non-Fermi liquid fixed points are stable or not, there will be a flow toward the superconducting instability. And eventually, we want to understand, this flow for some genetic UV theory so that we can understand the behavior of a particular UV theory under scale. And then hope is that even if non-Fermi liquid fixed points are unstable, this flow, vertical flow, is much faster than this outgoing flow toward the superconducting state, so that our theory flows close to the manifold of non-Fermi liquid fixed point, so that at some intermediate energy scale, the physics is controlled by this new critical theories. So in general, it's very hard to compute the beta functional of this coupling in the reliable way, mainly because this Yukawa coupling is strictly relevant, okay? Interestingly, in this particular theory, you can do that, at least in the limit that the nesting angle is small. It's non-zero, but small, okay? For example, this is I'm just showing that beta functional of the four-Fermion coupling in the pairing channel. So where electrons, say in segments 1 and 5, so 1 and 5 are the ones that are antipolar here, with momentum, say, k and minus k, scatter into the same segments with momentum p and minus p with some spin combination. And this is the leading order beta functional computed in the limit that the nesting angle is small. So this small nesting angle expansion is not the usual perturbative expansion. It's actually, in some sense, a strong coupling expansion. But we can show that this expansion is controlled. And the nice thing about this is that if you start with a small nesting angle, the quantum correction makes the nesting angle even smaller. So actually the theory flows toward the limit where nesting angle is 0. So therefore, your expansion becomes asymptotically exact. Okay? And then here, again, this -1 is due to the fact that this four-Fermion coupling has negative scaling dimension. And then the Z is the dynamical critical exponent because there's no Lorentz invariance. Time and space in general scales differently. And this eta is the anomalous dimension of fermion, because this is not Fermi liquid. Electron field acquires non-zero anomalous dimension, but anomalous dimension is momentum dependent, right? Because electron at the hotspot is more strongly coupled with the spin fluctuation. It has the largest anomalous dimension. And it is this, right? As if electron has a large anomalous dimension, that makes the four-fermion coupling more irrelevant. So that this incoherence of electron tend to suppress the superconducting instability. Okay, and here the dilatation in the momentum space is reminiscent to the fact that Kf is growing under the RG flow. Here, K and P are linear momentum, not angle. So it's a Kf times angle. So under the RG flow, effectively the momentum along the Fermi surface is stretched. So that's the dilatation. And I mean, here details are not important, but here the second line is a kind of mixing between different four-fermion coupling. Okay, so you know, in the CFT, we know that operator can mix into another operator that form a mixing matrix, right? And then if you diagonalize that mixing matrix, you get the scaling dimension. Here, operators are defined in the space of momentum along the Fermi surface. So it's there are continuously many operators. So therefore, mixing matrix is also infinite dimensional matrix. Okay, so this mixing matrix kind of mix this kind of coupling in different channel with a different momentum. Okay, in particular, one can show in this case the mixing matrix decays very slowly as a function of momentum, which shows the fact that interpatch scatterings are very important. Okay, you cannot ignore the large angle scatterings to fully understand the behavior of this coupling function. And there are BCS term, and also there are interactions that are generated by spin fluctuation. So this term here, third line, is independent of lambda. So that means even if you start with a zero four-fermion coupling, they are generated. So this is the part that has to do with the collective mode providing glue for the electron, right? So this collective mode provide attractive interaction for the electron, but at the same time, it makes electron incoherent. Okay, so one of the interesting questions that I wanted to understand is the competition between this incoherence effect and this glue pairing effect. Okay. Okay, so here, and here is the summary of functional RG flow. Here I have only kept nesting angle. This is still schematic because the full functional RG is in the space of coupling function, but this is schematic. So here I have nesting angle, and I have a four-fermion coupling because this is where the interesting action happens. So for now, let's ignore the imaginary part of the lambda. So this blue plane is the space of Hermitian theory, where couplings are such that your Hamiltonian is Hermitian. So this is the space of physical theories, right? So as I mentioned, the nesting angle actually become smaller and smaller under the RG flow. However, the flow of the four-fermion coupling is much faster than the flow of the nesting angle. So therefore, this RG flow looks almost horizontal. So before the nesting angle changes much, this four-fermion coupling changes a lot. So therefore, in order to understand the flow of the four-fermion coupling, it is a good approximation to regard the nesting angle as almost constant, although it's not although it still flows logarithmically. But then if the bare nesting angle is smaller and smaller, the flow is slower and slower, and such that there are real fixed points at this origin. So this is an interesting fixed point in that here the Yukawa coupling vanishes, but at the same time the nesting angle vanishes in such a way that their ratio is order of 1. Okay, so because of the competition between kinetic energy and the interaction, the kinetic term due to screening tend to suppress the interaction. On the other hand, interaction mix electron on different segments, assimilating their Fermi velocity, making nesting angle close to 0. So there's a fierce competition between kinetic term and interaction term. So in the low energy limit, at the fixed point, both of them goes to 0, but in a way their ratio is order of 1. And it is this ratio that determines the leading anomalous dimension. So for example, the boson has anomalous dimension 1. And this is exact because, as I mentioned, small nesting angle expansion become exact in the low energy limit. But in any case, for any non-zero nesting angle at UV, you can regard the nesting angle to be almost fixed to study the RG flow of the four-Fermi coupling function. And away from V equals 0, there's no fixed point, okay? So the coupling function actually exhibit runaway flow toward the negative infinity. So which signifies that the system is unstable toward superconductivity at low energy. If the UV theory has a non-zero nesting angle, if you don't fine-tune your nesting angle, that's what happens, okay? But then, to understand this RG flow within the space of real theory, it's useful to expand our scope by allowing non-Hermitian theory. Of course, these non-Hermitian theories are not physical theory, but it turns out that for each fixed nesting angle, this four-fermion coupling exhibit pairs of non-Hermitian fixed point. This red line represents the non-Hermitian fixed point at each fixed nesting angle. Okay, and then as the nesting angle becomes smaller and smaller, this non-Hermitian fixed point become closer and closer to the real axis, and they merge at the true fixed point in the zero nesting angle limit. Okay, so this is some global picture of the functional RG flow. And going back to the question of superconductivity, sorry, I wanted to show. Going back to superconductivity, yeah. So we can look at the functional RG flow in different channels. Okay, so because coupling function is infinite dimensional, it's hard to visualize, but you can look at the projected RG flow in some particular channel. So here, different RG flow here shown in this three graph represent the RG flow of the Hermitian and non-Hermitian component of the coupling function in some particular channel. So here on the leftmost channel is the channel where my Cooper pair has a very large weight at hotspot. So it's essentially a channel where for the hotspot electrons are dominant in my waveform, Cooper pair wave function. And surprisingly, in that channel, the fixed point arises on the rear axis. Okay, so there's at least in this channel, there's a stable fixed point and one unstable fixed point. So this means that the electrons right at the hotspot are not immediately susceptible to pairing instability. And this is due to the fact that at the hotspot electron acquires large anomalous dimension, So therefore, they are highly incoherent. So they are not very susceptible to pairing, although they are subject to the strongest attractive interaction. Okay. Now, as I make the weight of the hot electron smaller, this fixed point on the rear axis become closer and closer, and they collide at some particular choice of the Cooper-Pell wave function. And then if I include enough weight away from the hot spot, this fixed point for the four-fermion coupling bifurcate into the complex plane, kind of opening up the gate for the runaway flow. So in this case, for real theory, on the rear axis, the coupling flows to negative infinity. Okay. Of course, if I only include electrons far, far away from the hotspot, these 2 points again come back closer to the rear axis, because then electrons are not subject to the strong attractive interaction either. So there's some optimal weight between hot and cold electron that are most unstable. So the main message here is that superconductivity is driven not just by hot electrons, but through the interplay between hot and cold electrons. So what happens is that as we go to low energy, so here the horizontal axis is momentum along the Fermi surface. Here vertical axis is the energy. And here this color plot is the exponent with which the imaginary part of the single particle Green's function scale, right? So it's a scattering rate of single electron. And far away from the hotspot, so k equals 0 is the hotspot here. Far away from the hotspot at low energy, electrons obey the Fermi liquid-like behavior, omega square scaling. But at the hotspot, it's a sublinear, so they are non-Fermi liquid-like. And if you are a little bit away from the hotspot, as we go low energy, as we go down the energy, at high energy, the electrons are incoherent because they are strongly coupled with the spin fluctuation. But as it goes down in energy, eventually, in order for electron to be scattered onto Fermi surface, it requires interacting with the spin fluctuation at non-zero energy, right? So therefore, those coupling become weak at low energy. That's why at sufficiently low energy, electrons become coherent again. And it is those electrons that are not right at the hotspot, but like a worm. They have been very incoherent at high energy, but at sufficiently low energy, they emerge as a coherent excitation, but they are still come with a strong attractive interaction that has been generated at high energy. So it is those interaction that drives those lukewarm electrons into superconducting state. Okay, and then another point is that at a small nesting angle, because of the proximity to the fixed point and also this complex fixed point, the RG flow through this region is very slow. So you expect that superconducting transition temperature is suppressed in the small nesting angle limit. So here V is bare nesting angle and A is some universal number. So we expect that TC is suppressed in this way. Okay, sorry for the overtime. So in summary, in metals, in order to understand the low energy physics, in principle, you have to include the information about the entire Fermi surface. And this genetically gives rise to UVR mixing, where short distance physics interfere with the low energy physics. So as a result, a lot of intuition that we learn from relativistic field theory do not apply. For example, in constructing renormalizable field theory, you have to be more careful by including some coupling that are seemingly irrelevant, and they can actually play an important role in driving instability at low energies. Okay, thank you for your attention.
Thank you very much, Sung-Sik. Let me clap on behalf of the audience. Any questions? please unmute yourself and go ahead if you have questions.
Could I ask one, Walter, here?
Yeah, go ahead.
Okay. So besides BCS scattering and forward scattering, if your fermions have spin, there's also a process which you might call backscattering or so in one dimension, where the particles, okay, the two momenta of the ingoing particles remain the same, but they flip their spin. That is geometrically also possible at low energy. In the one-dimensional geology thing, this is a so-called G1 process. Is that process important? And or maybe you have taken it into account already? I'm not sure about that.
Yeah, I think we did. It is encoded. It is encoded in this spin dependence, I think.
Mm-hmm.
It is the particle pair with the spin, some general spin, scattered into particle pair with the same momentum with some another general spin, while the total spin is conserved. So there are, you can look at, I guess, spin singlet channel and triplet channel separately.
Okay.
And if the UV couplings has a different strength in these two channels, in general, one channel will be more important than the other. But essentially, they are we can consider each channel as a separate channel. So I think this solution still holds for each channel. This R represent either spin singlet or triplet channel, and then they are decoupled.
Okay. Yeah. Thank you. Interesting.
Any other question? I have maybe one question about the first part. So when you showed this sort of ideal Hamiltonian of the Landau theory, this one that only had the occupations, so to say, if I take this Hamiltonian literally as a quantum Hamiltonian, will it contain collective modes? Because it seems that all the eigenstates would just be, usual quasi-particles, just usual occupations, right?
I don't think so, right? Because, yeah, as you said, the Fermi surface, the quasi-particle number, in terms of quasi-particle, the shape of the Fermi surface rigid.
Yeah, exactly.
If I bend the Fermi surface, deform the shape, it will stay there. It's an eigenstate.
Yes. I think it does not contain the collective modes, right? So, I just want to maybe be a bit of devil's advocate, but then I would say that this Hamiltonian is not really Landau Fermi liquid theory, right? Because it's not equivalent to sort of the solutions of a kinetic equation, right? In some sense.
Yeah, I guess it is the zero energy limit of low energy, some low energy effective theory. So, in order to collective mode is, in order to describe collective mode at non-zero energy dispersing mode, right? You have to include the physics that are important away from strict zero energy limit.
Yes.
Here you have to include the scattering between particle pairs and so on. So,
but in a sense, if I use one of these theories of this sort of that only have forward scattering, these kind of bosonized theories of, they will contain the collective modes, right? But so in a sense, these theories are not exactly this same theory, right? In a sense, because they would contain the collective modes. Right?
So you have to somehow allow shape of the Fermi surface to fluctuate.
Yeah.
And yeah. but in some sense, it still encodes the
I think this theory is like taking those theories, but only including the Q equals 0 part, because those, you see, those operators that add sort of quasi-particles also have a sort of a Q that is associated with the spatial dependence, right? And this looks like the part in which you would sort of globally deform the Fermi surface in space, but without any kind of oscillation as a function of a space.
Yeah.
So I think this is like the Q equals 0 part of the theory, but it's not,
yeah,
it does not contain.
Maybe what is captured more in those earlier work on bosonization is the kind of momentum transfer in the radial direction. So here, no momentum transfer is captured at all. But in the bosonized theory, where you say number of particles is preserved at each angle, but still you allow particles to change their radial momentum. Okay. I think that is more than this. And probably that is still enough to capture some collective mode. But more generally, I think that is still not full story. That's
very good. Any other question from the audience?
If I may, still one. If you apply the same thing just in one dimension, what would you get? Would it be geology to second order in the couplings, or doesn't this make any sense?
Okay. So that's an interesting question. So I think if the Fermi surface was flat, then this Q doesn't have to be small, because electrons can scatter to anywhere on the Fermi surface. It's like yeah. So here, the fact that the Q had to be small here is due to the is due to the curvature of the Fermi surface, and say at angle theta and theta prime.
Right.
The generically, by absorbing momentum Q, fermions are inevitably kicked away from the Fermi surface. So therefore, that's why Q had to be small. But for flat Fermi surface, there will be no restriction in the magnitude of Q. So you will have to allow now momentum transfer to be also order of kf. Okay, so that yeah.
Yeah, not sure, but okay, maybe this might become a longer discussion.
Yeah, I mean, another way of saying, if this, instead of this spherical Fermi surface, it was straight like this, then electron at one location can be scattered tangentially by a.
Yeah, sure, but maybe it's easier to ask what happens if you have just two Fermi points. Of course, it's the same thing, in a sense, the same thing as having two parallel flat pieces, because in a sense, it's the same thing.
Oh, strictly 1D.
Yeah.
Okay, and then I guess you will have basically CFT, right? And
yeah, of course, there are other ways of solving that. And I was just wondering to understand better the level of approximation you have here, what you would get in one dimension. But it could be that this limit doesn't make any sense for your theory. So I'm not sure.
I mean, in one dimension, I guess the scattering would be always forward, almost by construction, right? Because there would be no
forward, and and then there's this backscattering, which, however, is also BCS at the same time in a sense. Sort of, if you have a right mover with spin up going to the left Fermi point and vice versa, then this can be viewed as a BCS, and that drives actually in one dimension a sort of pairing type instability leading to a gap, etc., which is similar to superconductor. All right. Yeah. Yeah, sometimes it's useful to think about this 1D as a special case. Sometimes it's not. So I'm not sure in this situation whether it makes any sense.
Yeah, I think in order to make contact, I tend to think 1D as a limit where Fermi surface become flat.
Yeah.
Then probably you can make some
connection.
Yeah.
Okay. Thanks.
So maybe if I could just ask one more thing, Sung-Sik, are you in a rush, by the way, that since we have kept you for a long time?
No, I'm okay. Yeah.
Just to kind of understand a little bit more this sort of discussion we were having at the beginning. So in a sense, if I want to understand correlation functions of particle Hall operators at very small, sort of asymptotically small q and omega, and I do the calculation with usual Landau Fermi liquid theory, I will get all these correlation functions correct up to essentially lifetimes or decay terms in some sense. Is that what you were trying to say at the beginning?
Okay, so what? I think this theory alone doesn't even captures the mixing between particle pairs created at different locations on the Fermi surface. I mean, right? So when you do it, when you compute those correlation functions, I think you implicitly go beyond this theory by allowing some processes where, for example, this particle pair can be scattered into other part of the Fermi surface, right? So that kind of process is especially when Q is non-zero, that process is absent in the strict fixed point action.
Yeah.
But those processes are important for the collective modes, and so I have to say we are not using actually this fixed point theory for that.
Right. But I have a very kind of naive sort of understanding, so I might be wrong. So let me just state it to see if you agree with this. So I was under the impression that if I sort of open, Pines and Nocieres, and I study a Fermi liquid in 3 dimensions, right, and I use the usual Landau kinetic equation calculations with Landau parameters, as long as I do calculations at sufficiently small q and omega, that will be exact in some sense. The Landau Fermi liquid theory will be exact at small q and omega if I keep all the Landau parameters. But then, is that true or not? And if it's not, then what is Landau Fermi liquid theory missing? What I think you mentioned at the beginning something about decay rates, but then maybe you can try to.
Yeah, I mean, for single particle excitation, for example, the lifetime of quasi-particle, of course, the scattering rate is subleading compared to the energy self. So it is not captured within the fixed point theory, of course. To make quasi-particle to decay, you need non-fold scatterings. Okay, so that is for that, if you want to capture that, you have to go beyond this strict fold scattering limit.
Yeah.
Yeah.
But my understanding is that that decay, you know, when you go to sufficiently Q and omega, at least for any kind of particle Hall pair correlator, is not important, right? At least in 3 dimensions, let's say, if we ignore 3 dimensions and higher, for example.
But the leading decay rate is T omega square. So if you want, it depends on what you want, I guess. If you want to, I mean, if you want to understand the leading term in the small omega limit, beyond the T linear term, then you need to include those non-forward scatterings.
I mean, is this something similar to, like, you know, in Latinger liquid theory, for example, if you are trying to compute some observable, like the conductivity, you know, if you have some kind of lattice model and you're trying to compute the conductivity that arises, let's say, from umklapp, right, at low temperatures, you know, if you don't have any kind of sort of, you know, higher order process that is scattering the fermions, let's say the right movers onto left movers, you will never compute a correct conductivity, right? Even though those terms, you know, when you add them to the Hamiltonian, they are sort of, I mean, I guess they are formally irrelevant. You're saying here these corrections are not irrelevant; they are marginal in some sense. So maybe it's not the same, but if I want to compute an actual conductivity from a lattice model in 1D arising from umklapp, I will have to include formally irrelevant terms to the Hamiltonian, just because, you know, the Hamiltonian doesn't have decay for the current just by itself in the Latinger model, right?
Yeah, it's like that, because
it's like that.
That is the leading momentum conservation breaking term, right? So
right.
Likewise, the leading term that creates a non-zero, you know, scattering rate is this non-forward scattering.
Right. I see. So is it like that in some sense then?
Yeah, I think so. I think so. Because this, from symmetry point of view, this lambda form liquid theory has the, you know, U1 symmetry at each momentum on the Fermi surface.
Right.
But at any finite energy, this non-forward scatterings break that symmetry to some extent, and they are the leading terms that creates non-zero scattering rate.
Right. That infinite U1 is not in the UV, so you need some kind of leading term to break it.
Yeah, that's right.
I see. Okay, very interesting.
I think for form liquid still, as we go to low energy limit, at least if the pairing interaction was repulsive, pairing interaction flows to 0, and you are left with this near forward scattering, but still as momentum, as the energy goes to 0, range of Q becomes smaller and smaller. So still this the number of particles effectively become conserved at every patch, right? But in non-form liquid, in general, that is not the case, because in non-form liquid, as I alluded, even in the normal state, the superconducting fluctuations are present, intrinsic superconducting fluctuation that are part of non-form liquid state. So, in other words, in this diagram, say, as the theory passed through this bottleneck region where the RG flow is very small. Yeah, maybe the previous picture is more there. So near this non-form liquid fixed point, there are intrinsic superconducting fluctuation where the four fermion coupling is not zero. And it also decays, power law in momentum transfer. So that means electron pair at momentum k minus k can be scattered into any other momentum on the Fermi surface, and the tail decays rather slowly, power law.
Mm-hmm.
So that qualitatively, changed the emergent symmetry even in the normal state. Yeah.
Okay. All right. Thank you very much, Sung-Sik.
Yeah. Thank you, Inti and everyone.
Yeah. Thanks everyone for coming.